sometimes when we're using something like uboot or uroot, you don't always have an operating system when you're running drivers. So sometimes you have to run bare metal drivers without an OS. And getting a more deep understanding of how bare metal drivers work with uboot requires some extended hardware. And Satish is going to tell you something about that. So give a warm round of applause for Satish Kumar.
Thank you all. Myself, Satish, I work for Cavium Networks. So I'm trying to give a talk today on understanding U-boot code with bare metal drivers using Xilinx FPGA board. So part of this, let me introduce the index set. So the thing is mainly what I'm trying to add is the difference between the U-boot code and the bare metal code, one thing, and how we are going to debug that bare metal code, and you can customize that code, right? Using that in a kind of bare metal level, you can customize. And the same thing, you can test it on the FPGA. That I'm trying to give it in a little deeper way with respect to a debugging perspective, so that it will be easy to understand like how actual driver has been written, because the functionality wise, either it can be core boot, it can be U-boot, or it can be whatever. The kind of a firmware is same. So how we are going to customize that, how we can reduce that is a matter. So there, that kind of support that we are trying to provide with respect to the FPGA. So I'm trying to give that talk today. So part of that, let me talk with respect to the U-boot code first. So I'm trying to capture kind of things, part of clock support, GPIO support, I2C, SPA, and timer support. So part of that, let me start with clock support. So it's a generic one because everyone knows that what actually these clock drivers do. So it's like a kind of a functionality that set rate, start peripheral, set enable, peripheral get rate. So the intention is, yes, the kind of things that it's a pretty basic thing, but how we are going to use this will be the different way that we will showcase. So if we can see this, the kind of the code presented in here in the clock.h and the clock.c, and the makefile is part of that AP directory. An example is, I can say that Tegra SOC vendor. Part of that, the clock.c is one kind of an example, which will talk about how the clock is being supported in the U-boot, right? So this is one thing with respect to the clocks. And if we talk about the GPIOs, which are pretty easy thing for any kind of a person which want to start. So GPIOs are used as input and output, and it can be read as 0 or 1 for the input, and it can be set as 0 or 1 for the output values. And yes, the interfacing stuff, GPIO request, GPIO free, GPIO direction input. So these are all the functions we have been interfaced when we are writing a driver in an U-boot code, right? So, and GPIO direction output, GPIO get value, and GPIO set value. So these are all the things for each function. They're having a separate kind of functionality that is providing. Let's say if I say GPIO direction output, makes a specified GPIO and output and sets its value. So these are all fine with respect to U-boot, yes, but my main concentration is how to use this in an FPGA board. So in this case, like say GPIOs are numbered from 0 with NM specified in the header file of GPIO.h, starting from 0 to the number of pins that it has been showcasing there. And then the additional functions, it is using the pin muxing and the pull up and the pull down registers. So that with that we can support the additional functionality in the GPIO driver. And then the corresponding header files will be provided in the SOC vendor /GPIO.h, and the example driver will be GPIO of maybe the Tegra.c or whatever, and the corresponding make file and the example file we are showcasing there. Same way I2C support. So I2C support, again, the functionality we are using is I2C set bus number, I2C get bus number. So get bus is used to obtain the current bus, and set bus is used to set the bus for the current transition, where we are trying to do the read and write things will be happen with respect to the set bus number. Again, the header files, the implementation file, the example file where it is been mentioned. So again, the header file will be include I2C.h, and the implementation file will be drivers I2C driver name.c, and the make file. And the example is again Tegra SOC. I have taken it. Again, SPA flash. So SPA flash is again a kind of SF read, SF write, what we are going to use here. So this is again, it is used to store the firmware where we are trying to keep the actual piece of code that which we want to load it into the U-boot, right, before U-boot. So again, these are the functions that we are using and the structure we are using that to initialize in the uboot code, right? So now SPI flash support in the uboot, yes, we are using a include SPI flash.h and the implementation file and the make file and the example file. So these are all the things which we really see, and even the timer support, timer init and get timer. And here is one more thing is timer get us, which actually gives you the boot time. Initially, if you want to track how much time it is taking to boot a board, so we can use that timer underscore get us. So with that, and yeah, timer support in uboot with respect to that, where these features, these files have been presented. This is all we are showcased. So till now, what we are showcasing is the generic code presented in the uboot code. So now, once from here, if we are going into the bare metal drivers, we can see that how it is being defined. The same kind of functionality. Let's say when I'm talking about the timer code of RCOM S5P common timer.c, if I want to debug the same code in the bare metal, so how it will be. So that's where like the actual talk will be coming into picture. So for debugging that, we are using a board called the Jet board, which is coming from the Xilinx. So it is a support of FPGA, so that I can customize that SoC, or I can customize IPs presented on the board, and I can write a bare metal driver. I can customize it to some extent of whatever the areas we need, and all those things that we will see. So part of that, let's take the startup code. As we are having a and for this one we are using an Eclipse kind of method. So there actually, one thing that FPGA board which we are showcasing here. So one thing is it is having the XMD, Xilinx microprocessor debugger, which is actually works like a JTAG debugger, but this provides the node locker license. Kind of it will be connected to a one device or one laptop, you can say. So it's been a constant one. You cannot change it to the other one. So with that, we can debug or we can customize the entire SoC code starting from the uboot level. So part of that, if we take that, so I'm taking the code that which has been a bare metal code, let's say the SPL code or whatever you can say the name. So from that, I'm trying to identify the boot mode register, and it will getting into the PS7 init. So these guys, this PS7 or the PL is the kind of terminology used by the Xilinx. This is the kind of PS means processing system, and PL means programmable logic. So when we are using any FPGA supported components, they called as a PL, and if it is connected part of the board itself, they call as a PS, processing system. So as part of this, we can see that the first level of debugging code, we can see that initialization of the MIO, multiplex IOs, PLLs, clock and EDR. So once we are trying to debug that code, we can see from each code level, or the intention is we cannot basically see the code debugging in this area with using a regular debugger, right? But as we are using an FPGA board and it is being into bare metal drivers, so same thing that we can do debug the same using these FPGA boards. That is the main thing. So here get silicon version. From there, if we are debugging, it is getting into the what type of version it is. So if it is equal to 1, 2, 3, or today it is even a 5, version number 5 also. So now if it is version 3, if it is matching that, with that it is getting into the other area where I am doing my MIO initialization, PLL initialization, and then clock initialization, DDR initialization, and peripheral initialization. So once we are saying about this peripherals initialization, the regular uboot code we see, like what are all the registers we are initializing for all the devices. Let's say if I'm taking I2C, so all the register values what we are initializing, same thing in the bare metal code we are providing in this part of the code. So from here, from the peripherals init data, if we are entering into the next level, we can see that all the code has been registered over there. The values has been given to that. So now I'm taking one. So this is all what we have seen is the board initialization code. So part of this, one of the peripherals I'm taking a GPIO as an example. So part of this, I can see that there is an example code which is of, I can see, this is just a basic bare metal code. You can see over there. Okay, yeah. So the thing is trying to compare now the basic GPIO driver written in the U-boot code and how it is being written in a regular bare metal code. So I just captured a kind of screenshots which will be defined here. It's interrupt driven mode operation, but anyway, the GPIO driver should be initialized with respect to the corresponding device ID and the lookup config table, because each will be registered with a unique device ID. With that only it will go ahead. So this is a GPIO device ID we are talking about. And then there is a GPIO interrupt example, but yeah. So this is the main function. What we are trying to do is GPIO interrupt example test. With that, if we can get inside, okay, GPIO interrupt example, the intention of adding this screen is we can see that this function shows the uses of interrupt functionality of the GPIO device, and it is responsible for initializing the GPIO device, so that before I'm trying to initialize my interrupt ID, before that it is taking care of initializing your GPIO device also. After that, it is going into the interrupt mode. So yeah, this is the actual bare metal code where it is trying to add one config pointer and one GPIO PS lookup config. So this X GPIO PS or X ST, these are all kind of terminology for the Xilinx, just X, right? So after that, if we see GPIO PS lookup config, if we get inside of that, what actually it is doing, we can identify that, okay, set direction, set output enable, and set up interrupt system. So if we can see that set direction and the set direction output, set output enable, these are all the functions that what we have seen in a U-boot code. What are all the functions we have mentioned in the regular driver code? The same one, the terminology might different, but if you can see the set direction, set output enable is equivalent to the one that which we have earlier seen in the U-boot interface driver, right? So now we are entering into the interrupt handler function. But before that, yeah, this is a setup, and this is the total main.c code, bare metal code. So now, if I'm trying to debug that same piece of bare metal code, from where to where it is going. So like the first one is the Xilinx printf code, I mean the printf function it is being called. So from here, it is getting into the printf.c. If you can see there, right? So there is a Xilinx underscore printf.c. Part of that, it is taking each character as a regular single character wise. It is taking each character. From there, it is trying to print whatever the test code we have written here. The GPIO interrupt example test, each character has been sent out over there. So part of this printf code, here I'm taking each character and then I'm putting it onto the through the UART terminal. Right? This is just a printf code. And then once that is done, we are trying to get the GPIO interrupt example. From this, we are initializing the interrupt controller GPIO device ID and the GPIO also. So now, yeah. So this is the one that where the lookup config function, which we are in a regular U-boot code, we are initializing, or we are saying that yes, this is my device ID. So for that, here we are initializing all the device IDs part of this lookup config, and it is been searching where actually your GPIO is been initialized or not. If so, where it is. So that part will be taken care by this lookup config function name. So if we get inside this lookup config, it's been mentioned there, looks for the device configuration based on the unique device ID. So once it is get inside, we can identify that, we can see that how it is going to debug that. So part of that, it will search for the device where it is being presented, and it is been matched to that. And if it is presented over there, then only it will go to the next step. So it's a kind of same thing as how a regular U-boot or any driver will do. So here we are trying to showcase the same thing in the bare metal, so that it can be gives the better understanding, and the functionality wise we can make the changes as per the requirement. So now we can see that the config pointer has been placed over there on the other side. Once that lookup config function has been returned, that been checking with the null value, and then it's getting inside of that configuration initialization. So that it's like try to map that regular U-boot driver code with respect to this bare metal code, and then we can identify that matches, right? And this is the interrupt process testing part. Okay, part of that, let's get into the other area. Yeah, it is finding out the how many number of maximum banks it is having, and then GPIO config base address. Yeah, so these are all part of, again, the interrupt example, like whatever the interrupt testing we are trying to check it out. So with that, it is going inside. Okay, that's it. Yeah. So this is basically what we are trying to identify here is what are all the things that we have written in the uboot code. The same thing we are trying out in the bare metal, and we're pushing that into the an FPGA board and trying to debug, because the kind of uboot code which we cannot debug instead of with respect to a JTAG debugger, but yes, in a bare metal level we are trying to debug the same using a XMD debugger, and so it can give a lot of options that to change the code or to see the code internally, whatever it has been written, and debug the things in a better way, right? So with that, yes, I think I have closed it very soon. I thought it is, I have a lot of slides, but yeah, I think yeah, fine. I think, most of the people have been with Linux boot, core boot and all. Maybe I didn't see much people with uboot. I'm not sure how much it is being connected, but yeah, the intention is when you are writing a pretty new uboot code for any new board, this is the one that we usually do for any Xilinx board or Cavium boards. So then, so this is where like you can get a more understanding, or we can debug the code in the initial level, and we can customize the IPs over there with respect to that jet board, whatever the board that we have showcased. Yeah, with that, I'm closing. If you have any questions, yes, I'm ready to answer.
Thank you. Let's have another round of applause. This was really fast. I didn't expect it to be that fast. But this again means that we have a lot of time for questions. So just same games as always. Just line up at the microphones and then ask your questions. Take your time.
Yeah.
More for the audience rather than you. Who here actually uses FPGAs and raise their hand?
Yeah, that's a difference coming. Yeah.
Okay.
So no one uses FPGA here.
I use it as a hobbyist, but I'm giving a talk tomorrow.
Okay.
Yeah.
Okay, fine. Thanks. Okay. So yeah, the thing is actually, once we are coming into the FPGA, of course, I have done this on a hobbyist project only, as I have my own FPGA. So the intention is, the customization of SoC, and you can write a lot of drivers over there. I mean, the way that we can test it, those drivers, it will be pretty good actually in a very early stage. And you can add whatever the driver you want, and you can delete whatever the way. If I want to add the timer in the initial level, I can add it. If I want to add one more interrupt controller, the other ways, those things and all is possible over there. And we can get the bare metal code from the Xilinx, and yes, we can write it on our own way, and the same thing we can push it to Xilinx SDK, which is a kind of Eclipse debugging mechanism, which I have shown now. So this is all done through the Eclipse with XMD. And if you have any questions, yes. Okay. If people are if they guys use the FPGA boards, might it will be more familiar.
Okay, well, this seems to be a very niche topic, but anyway, thank you very much.
Yeah.